morning, students. Today we will learn the weak duality theorem, which is a theorem which shows a relationship between the feasible solutions of the primal vis-a-vis the dual. The outline of today's talk is as follows. First of all, we will learn what is the meaning of asymmetric primal dual. You remember, in the last lecture we had learned the definition of a symmetric primal dual problem. Today we will learn what is the definition of a asymmetric primal dual problem. We will take an example, and after that we will learn the weak duality theorem, its statement and its proof in two ways. Then we will look at some of the results that can be derived from the weak duality theorem. Finally, I would like to give you an exercise as an homework. So, the first thing we need to learn is the definition of a asymmetric primal dual problem. This can be understood with the help of the following example. Suppose we have to write the dual of the following linear programming problem, that is, minimize f which is equal to minus 2x1 minus 3x2 plus 4x3. This is subject to 3x1 plus 6x2 minus 7x3 greater than or equal to 2, and the second constraint is twice x1 plus 5x2 plus 4x3 is equal to 4. x1, x2 and x3 are all greater than or equal to 0. Now, in this problem we find that this is not in the standard form of the primal, or it is not in the standard form of the dual, because if you recollect from the previous lecture, the primal standard form is minimization of objective function and greater than equal to type constraints, or maximization of objective function and less than equal to constraints. But in this given problem we have the second constraint as an equality. Therefore, we need to think what we can do about it. One suggestion is we can rewrite the second constraint like this, that is, twice x1 plus 5x2 plus 4x3 less than or equal to 4, and similarly twice x1 plus 5x2 plus 4x3 greater than or equal to 4. That means, we have written the equality in terms of both the conditions, that is, greater than as well as less than. Since we are going to take the intersection of all the constraints, automatically if we impose these two constraints, then the equality will be satisfied. But still now it is not in the standard form. So, therefore, what we need to do? We need to write it in the standard form, and the second constraint has been replaced by these two constraints, where one is with the less than sign and the other is with the greater than sign. However, since it is not in the standard form, we need to convert all the constraints in the greater than type. Therefore, we will convert the second constraint like this: minus twice x1 minus 5x2 minus 4x3 greater than or equal to minus 4. Why we have done this? We have done this because we have to convert the problem in the standard primal or the standard dual form, and with the minimization we need to have the constraints of the type greater than or equal to. So, therefore, the second constraint is now converted to greater than or equal to type, and that is what we get. We get 3 constraints, all the 3 constraints are of the greater than equal to type. Of course, x1, x2, x3 are all greater than or equal to 0. Please do not worry about the right hand side being negative, because at the moment we are not bringing it in the standard form for solving the problem by the simplex method. We are only interested in converting the given problem in the standard form of the primal. So, now that we are ready with the primal form, the standard form of the primal problem, that is, we are having the objective function as minimization of minus twice x1 minus 3x2 plus 4x3 subject to 3x1 plus 6x2 minus 7x3 greater than or equal to 2, and the second constraint is minus 2x1 minus 5x2 minus 4x3 greater than or equal to minus 4, and the third constraint is twice x1 plus 5x2 plus 4x3 greater than or equal to 4. This is in the standard form for the primal, and now we are ready to write its dual. So, as before, we will write the dual as follows. The objective function will become maximization, and the right hand side coefficients of the primal will become the coefficients of the objective function. So, therefore, the color code indicates that the right hand side entries of the primal, that is 2, minus 4 and 4, they will be the coefficients of the objective function, and that is what is happening. So, we will be maximizing twice y1 minus 4 y2 plus 4 y3, right. Again, the conditions on the inequalities, the coefficients have to be changed as far as these aij's are concerned. So, the transpose has to be taken, the rows becomes the columns and the columns becomes the rows. So, therefore, we should have 3 y1 minus 2 y2 plus 2 y3 less than or equal to minus 2. Similarly, 6 y1 minus 5 y2 plus 5 y3 less than or equal to minus 3, minus 7 y1 minus 4 y2 plus 4 y2 less than or equal to 4, and all the 3 variables y1, y2 and y3 are greater than or equal to 0. The cost coefficients of the primal have become the right hand side of the dual, as is being indicated with the color coding. So, is this all? My question is, should we be satisfied by this form of the problem or not? So, let us look at if we can simplify it further or not. Can you make an observation by which we can further simplify this dual? I am giving you the hint regarding the coefficients of y2 variables and y3 variables in the entire dual. Yes, that is right. You can observe that the coefficients of y2 and y3 are the same. Therefore, what we are going to do is the following. We are going to replace y2 minus y3 variable by another variable, let us say y star, in the entire problem. So, once we do this substitution, we will be left with 2 variables in the dual instead of the 3 variables in the dual. So, therefore, what do we get? We get the following problem: maximization of 2y1 minus 4y star subject to 3y1 minus 2y star less than or equal to minus 2, 6y1 minus 5y star less than or equal to minus 3, minus 7y1 minus 4y star less than or equal to 4. Of course, y1 is greater than or equal to 0 and y star is unrestricted in sign. That is, y star could take either positive values or negative values. So, that is what is the trick behind the entire substitution, that we have substituted y star in place of y2 minus y3. What is the benefit of this? The benefit is that we have reduced the number of variables from 3 to 2 and we have got a relationship between the primal and the dual. Now, the question is, what is that relationship? The relationship is that corresponding to the equality constraint of the primal, we have a unrestricted variable of the dual. Because let us go back to the problem. The given problem was this, that is, in the second constraint we had the equality. In the second constraint we had the equality, and therefore, the equality constraint of the primal is reflected as a unrestricted variable in the dual. Let me repeat, the equality constraint of the primal is reflected as a unrestricted variable of the dual, and that is what is happening here. If you look at the final dual that we have, y star is the dual variable which is unrestricted in sign, and this is corresponding to the equality constraint of the primal. Okay. Another example, suppose we want to write the dual of the following problem. The problem is minimization of minus twice x1 minus 3 x2 subject to 3 x1 plus 6 x2 greater than or equal to 2, and the second constraint is twice x1 plus 5 x2 greater than or equal to 4, x1 is greater than or equal to 0, whereas x2 is unrestricted in sign. Now, this is the primal that is given to us and we have to think how we can write its dual. As you know that when you have an unrestricted variable, it can be represented as the difference of two variables which are both greater than or equal to 0. So, we are going to make this substitution. Substitute x2 is equal to x3 minus x4 in the entire problem, and we know that x3 and x4 should be greater than or equal to 0. So, with this substitution, although we will be increasing the number of decision variables from 2 to 3, but the advantage that we will get is that all the decision variables will be greater than or equal to 0. So, we make the substitution in the entire problem, and that is the problem that we get. We get minimization of minus 2x1 minus 3x3 minus 3x4 subject to the conditions again where we have substituted x3 minus x4 in place of x2. This has to be done in the entire problem, and of course, we have to make sure that x1, x3 and x4 are all greater than or equal to 0. Now, this is the primal in the standard form. Now, we are ready to write its dual. So, the dual is as follows: maximization of twice y1 plus 4 y2 subject to minus 3 y1 plus 2 y2 less than or equal to minus 2, 6 y1 plus 5 y2 less than or equal to minus 3, minus 6 y1 minus 5 y2 less than or equal to minus 3, and y1 and y2 are greater than or equal to 0. So, we have now successfully written the dual of the given problem. But is there a way in which we can simplify this problem further? If you observe the constraints, you will find that the second constraint and the third constraint have a relationship. And what is the relationship? That is, you can write them as an equality. So, here you are. The second and the third constraint can be written as 6 y1 plus 5 y2 is equal to 3, and y1 is greater than or equal to 0, and y2 is an unrestricted variable. So, with the help of this example, I hope we have understood what is the way in which the unrestricted variables of the primal are related with the equality constraints of the dual. Now, let us look at what do we mean by the weak duality theorem. This theorem is stated as follows: the value of the objective function f(x) for any feasible solution of the primal, which is in the form of the minimization type, is greater than or equal to the value of the objective function, let us say w(y), for any feasible solution of the maximization dual. In other words, the theorem states that f should be greater than or equal to w. Please note that the primal should be in the minimization type, and of course, the constraint should be greater than type, and the dual should be of the maximization type, and the constraint should be less than equal to type. Only then this condition f is greater than or equal to w will be satisfied. So, this is the theorem, it is a very famous theorem, and it tries to give you a relationship between the feasible solutions of the primal and the dual. Please note, they are not necessarily the optimum solutions, they are the feasible solutions. So, we need to find out the proof for this. Here is the proof. Let us suppose that the primal problem is given by minimization of f(x), which is equal to c1 x1 plus c2 x2 plus cn xn, and this is subject to a11 x1 plus a12 x2 plus a1n xn greater than or equal to b1. Similarly, am1 x1 plus am2 x2 plus amn xn is greater than or equal to bm. All the xi's are greater than or equal to 0. So, this is the standard form of the primal, where the objective function is in the minimization type and the constraints are in the greater than type. Now, the corresponding dual of this problem can be written, but before with that we will need to introduce the surplus variables, because we have the greater than constraints. So, the greater than constraints have to be converted into the equality type. Therefore, we need to introduce the surplus variables in the primal, and we get the following problem: minimization of C1 x1 plus C2 x2 plus Cn xn subject to A11 x1, A12 x2, A1n xn minus xn plus 1. Please note, we have to introduce this purple colored variable, which is nothing but a surplus variable. Now, the surplus variables have to be added into each of the constraints, and they not added, they have to be subtracted from each of the constraints, because in the primal our constraints were of the greater than equal to type. Since we have to convert the greater than equal to type to the equality type, we need to subtract the surplus variables, and once we have done this, then all the constraints are converted into equality type. Therefore, we have the decision variables x1, x2, xn, xn plus 1 up to xn plus m. All of them will be greater than or equal to 0. Now, coming to the dual of the problem. The dual of the problem can be written as maximization of w of y, which is equal to b1 y1 plus b2 y2 plus bm ym, and this is subject to the conditions of the type less than equal to C1. So, you have a11 y1 plus a21 y2 plus am1 ym less than or equal to C1. So, all these constraints are of the less than equal to type. Of course, the decision variables yi's of the dual have also to be greater than or equal to 0, and they are m in number. Again, we need to convert the constraints of this dual into equality, and for doing this we need to add slack variables to each of the constraints. Therefore, we will add slack variable y m plus 1 to the left hand side of the first constraint. Similarly, we will add y m plus 2 to the second constraint, and like this. And finally, we get a system of equations which are all in the form of equality. So, what we have done basically, in the primal we have subtracted the surplus variables to make the inequalities into equalities, and similarly in the dual we have added the slack variables to convert the less than equal to sign equal to the equality sign. Of course, all the variables have to be greater than or equal to 0. Now, let us suppose that x1, x2, x n plus m be any feasible solution of the primal, because remember we have to show the condition for any feasible point. So, let x1, x2, xn plus m be any feasible solution, and similarly let y1, y2, ym plus n be any feasible solution of the dual. Now, we will multiply all the primal constraints by the respective variables y1, y2, etc. That is, the first constraint will be multiplied by y1, second constraint will be multiplied by y2, etc. And all this will be added. Similarly, we will multiply all the dual constraints by their respective variables, that is x1, x2, etc. That is, the first constraint of the dual will be multiplied by x1, the second constraint will be multiplied by x2, and so on, and they will be added. Now, we get two equations corresponding to the first and the second, and when we do this, we subtract one from the other. So, these two equations have now to be subtracted, and on subtracting we get the following. We get f minus w is equal to x1 times y m plus 1, x2 times y m plus 2, and so on. Now, if you observe the right hand side of this equation, what do you find? Yes, you find that all the variables on the right hand side are greater than or equal to 0, because that is what they are, the primal variables and the dual variables. None of them is unrestricted in sign. All of them are greater than or equal to 0. Therefore, the right hand side is greater than or equal to 0, and this implies that f is greater than or equal to w. Hence, we have proved the theorem that for any feasible solution of the primal and any feasible solution of the dual, we have the following relationship, that f is greater than or equal to w. Please note, in particular, what happens? Minimization of f x is greater than or equal to maximization of w y, where x is the primal feasible and y is the dual feasible, because this result is actually a corollary to this theorem, because this theorem is applicable for all feasible solutions, and therefore, since minimization has to be taken over all the feasible solutions, hence this corollary follows from the theorem immediately. Alternatively, we can write the proof of the theorem as follows. Let the primal be minimization of f x equal to c x subject to a x greater than or equal to b, x greater than 0, and dual be maximization of w y equal to b y subject to a y less than or equal to c, y greater than or equal to 0. Now, adding surplus variables to the primal and slack variables to the dual, we get a x minus x 1 is equal to b, where of course your x 1 should be greater than or equal to 0, they are the surplus variables, and similarly a y plus y 1 should be equal to c, where y 1 is greater than or equal to 0 are the slack variables. Now, for this is basically the way in which we can prove the theorem in the vector notation. So, I hope you understand that capital X stands for small x 1, x 2, x n, capital Y stands for small y 1, y 2, y m. Now, let x naught and y naught be feasible solutions to the primal and the dual respectively. Therefore, we can substitute this in the given conditions, and we get a x naught minus x 1 is equal to b. Similarly, a y naught plus y 1 is equal to c. Now, we will multiply the first equation by y naught, and we will be taking their sum and add second equation by x naught, and then we add them and we get a x naught y naught minus x 1 y naught is equal to b y naught, that is the first equation. Similarly, a y naught x naught plus y 1 x naught is equal to c x naught. Now, subtracting the first equation from the second, we get f minus w is equal to c x naught minus b y naught, which is equal to y 1 x naught minus y x naught y naught. Now, the right hand side, as you know, is all greater than or equal to 0, because they are the primal variables and the dual variables. Hence, f is greater than or equal to w. So, this is just another alternative way in which the weak duality theorem can be proved. Now, we have some results which can be derived from the weak duality theorem. The first corollary, I will call it as corollary 1, is as follows. The value of the objective function of the maximum primal problem for any primal feasible solution is a lower bound to the minimum value of the dual objective. So, therefore, the weak duality theorem gives us a lower bound for any feasible solution of the dual objective. Similarly, we can write corollary 2 as follows. The value of the objective function of the minimum dual problem for any dual feasible solution is a upper bound to the maximum value of the primal objective. The idea is that these two corollaries give us a lower and an upper bound for the primal and the dual respectively using the theorem, and they are intuitive and follow directly from the theorem. Another interesting corollary is the third corollary, that is, if the primal problem is feasible and its objective function value is unbounded, that is, if f is going to plus infinity, then the dual problem has an infeasible solution. So, till now we have not been talking about the unbounded case and the infeasible case, but the third corollary tells us the relationship between unbounded solution and infeasible solution of the primal and the dual respectively. That is, if the primal problem is there which is feasible and its objective function is going to infinity, that is, it is unbounded, then automatically the dual will be infeasible. Now, this needs some clarification. Therefore, let us take a primal and a dual. So, the primal is a simple two variable problem, that is minimization of twice x 1 minus 11 x 2 subject to twice x 1 plus 3 x 2 greater than or equal to 6, and the second constraint is minus x 1 is greater than or equal to minus 5. Both x 1 and x 2 are greater than or equal to 0. Now, if you write the dual of this problem, the dual of the problem is maximization of w is equal to 6 y 1 minus 5 y 2 subject to twice y 1 minus y 2 less than or equal to 2, 3 y 1 is less than equal to minus 11, and y 1 and y 2 are greater than or equal to 0. Next, let us look at the solutions and see what happens in the solutions. So, there are the solutions of the primal and the dual respectively. What do you find? you find that the objective function value of the primal is unbounded. Here you can see that the objective function value is going towards infinity, plus infinity in fact. It is going to plus infinity. It is going towards the upward direction, as is being indicated by the family of straight lines which represents the objective function. Of course, the domain is feasible, but the objective function value is going to infinity. This is the primal. The feasible domain is unbounded and it is feasible and unbounded, and objective function is going to infinity. Now, if you look at the dual can be plotted, and you can see clearly that the dual is infeasible. The dual has an infeasible solution, and therefore, what we had mentioned in the third corollary, that is, if the objective function goes to infinity of the primal, then the dual will become infeasible. Okay, the corollary number 4. If the dual is feasible and is unbounded, that is W goes to minus infinity, that is it is unbounded in the negative direction, then the primal problem is infeasible. So, here again let us look at this dual and its corresponding primal. The dual is f is equal to 3x1 plus 8x2 subject to minus 2x1 plus x2 less than or equal to 2, x2 is less than or equal to 4, x1 and x2 are greater than or equal to 0, and the corresponding primal is minimization of W is equal to 2y1 plus 4y2 subject to minus 2y1 greater than or equal to 3 and y1 plus y2 greater than or equal to 8, and y1 and y2 are greater than or equal to 0. So, we need to check the solutions of both the dual and the primal. So, the dual should be unbounded. Let us see whether it is unbounded or not. Yes, here are the graphs. You can look at the graphs and you find that the feasible domain of the dual is unbounded and the objective function value is going to minus infinity, and on the other hand the primal is infeasible. Hence, it can be clearly seen that the corollary 4 is satisfied. What about the converse? Now, the converse is also true. How? Let us look at note 5. If the primal is feasible and dual is infeasible, then primal is unbounded, and also if the dual is feasible and the primal is infeasible, then dual is unbounded. So, both these notes are related to the converse of what we had done in the corollary 3 and the corollary 4. Okay, so, with this we come to an end of this lecture, but before I depart, I want you to write the primal and the dual and also try to find out the solutions of the primals and the dual, and then in the next lecture we will see what other relationships exist between the primal and the dual. So, we have an exercise for you, that is, write the dual of the following LPP and what can you say about the solutions of the primal and the dual. Try to find out the solutions of the primal and the solution of the dual and see if you can find out a relationship between the two. So, the problem is maximization of z is equal to 3x1 plus 4x2 subject to 7x1 minus 2x2 greater than or equal to 4 minus 3x1 plus x2 less than or equal to 3, and x1 is greater than or equal to 0, whereas x2 is unrestricted in sign. Remember, in the symmetric problem, we have all the constraints are of the inequality type and all the decision variables are greater than or equal to type. However, in the asymmetric cases, this need not hold. There could be a situation where the constraints are of the equality type and the constraints and the decision variables are of the unrestricted type. And in this example, it is given to us that x2 is unrestricted in sign. So, I wish you all the best and try to find out the solution of the primal and the dual. Thank you.